Howdy, today I'm Flippin Science looking at testing alcohols and aldehydes. So the key ideas in intended student learning, distinguishing primary and secondary alcohols using acidified dichromate, so to describe how that happens. And since ketones can't be oxidized, we can use the Tollens test to determine between them. So that's what we're going to be looking at today. So we're going to look at two tests and how we can use them to distinguish between primary, secondary, and tertiary alcohols. So primary alcohols, just revision. Primary alcohol, the hydroxyl group is attached to a carbon that's attached to one carbon, or a hydrogen in the case of methanol. Secondary alcohols, the carbon that the hydroxyl group is attached to two carbons, and in tertiary, the carbon that's attached to the hydroxyl group is attached to three carbons. So the product that you get when you oxidize an alcohol depends on whether it's primary or secondary. Tertiary alcohols don't oxidize. Primary alcohols, like we have here, they oxidize to an aldehyde, and then that aldehyde further oxidizes onto a carboxylic acid. Secondary alcohols oxidize to ketones. So we've got the ketone group is the carbonyl group, but it's in the middle of a chain. Whereas with an aldehyde, the carbonyl group is at the end of a chain. And then, like I said, that further oxidizes to a carboxylic acid. The oxidizing agent we're using in this is called acidified dichromate solution. You can use many different oxidizing agents to do this, oxidation of primary or secondary alcohols. We're specifically looking at acidified potassium dichromate because it has a pretty color change that we can use. So primary and secondary alcohols, when we mix them with acidified dichromate, they oxidize the dichromate ion to chromium ions, and when that happens we get a color change. Dichromate ions are an orange color, the chromium ions are a green color. So if you have a primary or secondary alcohol, you mix it with acidified potassium or sodium dichromate, the solution, once it's warmed, will turn from orange to green. Tertiary alcohols, since they don't oxidize, the chromium ions don't change from dichromate to chromium ions, so the color remains at the orange color. So here's a half equation showing the reaction of the dichromate ions turning into chromium ions. It's a reduction reaction, so the dichromate ions are reduced to chromium ions, and like I said, the color change is orange from the dichromate to green from the chromium ions. This is a reduction. It causes oxidation, so the alcohol, if it's primary or secondary, is oxidized. It's oxidized to an aldehyde and then carboxylic acid if it's primary, and to a ketone if it's secondary. Like I said before, the reaction is a bit slow, so we need to warm up the reaction vessel when we do this. So the products of oxidation of primary and secondary alcohols are immediately aldehydes and ketones. So immediately aldehydes for the primary alcohol and then ketones for the secondary alcohols. Ketones don't readily oxidize further on, but aldehydes do. The fact that aldehydes do is what we can use to determine if our mixture contains an aldehyde or a ketone. We're going to be using Tollens reagent. If you want to extract the aldehyde directly from your reaction mix where you're oxidizing a primary alcohol, you need to extract it directly, and often we do this using a distillation apparatus, so that as soon as the aldehyde forms, it distills off. Otherwise, the aldehyde will just oxidize through to the carboxylic acid. So if we oxidize an aldehyde in acidic condition, we get a carboxylic acid. So here we have the primary alcohol goes to aldehyde, goes to carboxylic acid. So down here I've got a bit of a question. What would the oxidation products of butanol be in acidic conditions? So have a think about it. So the oxidation products of butanol, initially it will be butanal. Butanal, yes, that's at the end of the chain, so we don't need to number that. And then finally butanoic acid. So in acidic conditions you get the carboxylic acid. When an aldehyde is oxidized in basic conditions, however, we don't get the carboxylic acid because it ionizes straight away, and we get a carboxylate ion. So we get C double bond O, O minus. If we have a base around like sodium hydroxide, then we'll get sodium sticking to that if we were to evaporate off the water. But we get this negative carboxylate ion produced in basic situations. This will be similar to what we see in esters a bit later on, so this is worthwhile learning. So in acidic conditions you get the carboxylic acid, in basic conditions you get a carboxylate salt. So the carboxylate ion that can then produce a carboxylate salt. So as I was saying, the test is called the Tollens test. We use Tollens reagent, which is ammoniacal silver nitrate. If an aldehyde is present, the aldehyde reacts with the ammoniacal silver nitrate and you get a silver mirror forming on the walls of your reaction vessel. You don't need to know the reaction equation, but you do need to know what the products of the test are. So if you have an aldehyde, you mix it with the ammoniacal silver nitrate, which is this stuff here, you get your silver forming, so that's the 2Ag here. And we can see here on the reaction vessel, in this case a test tube, we get this nice silver mirror. So you mix your mix containing the aldehyde with the ammoniacal silver nitrate. Again, you warm it for a little while because that increases the reaction rate, and you'll see a silver mirror forming on the reaction vessel. So that silver mirror, that's a thin layer of solid silver, and this is how mirrors were made for a very long time. Nowadays, aluminium is used instead. What you would do is you would get a piece of glass, you would coat it with formaldehyde, which is methanol, which is an aldehyde, and then you'd spray that glass coated with the methanol with Tollens reagent. You warm it up for a little bit, and then you get a thin layer of silver, and that covers the glass, and that's where you get your mirrors from. So let's have a look at some questions. So the structural formula of two monosaccharides, A and B, are shown below. Identify which one of A and B would react with Tollens reagent and state the observation that would indicate a reaction had occurred. So if we look at A is an aldehyde. At the end of the chain we've got the carbonyl group, C double bond O. If we look at B is a ketone, so we've got the carbonyl group. It's not at the end of the chain, it's in the middle of the chain somewhere. So what that means is A is going to react with Tollens reagent because it's an aldehyde, and the observation would be the formation of a silver mirror on the reaction vessel wall. Here's another few questions. So gingerol, component of ginger, can be used to reduce inflammation. Here's the structural formula. Name functional group 1. So we have a carbonyl group. It's in the middle of a chain, so that makes this a ketone group. So it's a carbonyl group, but it's a ketone. Question 2, state the color. A sample of gingerol was mixed with acidified dichromate solution and warmed. Color change occurred. State the color of the mixture after warming. So acidified potassium dichromate, that will react with primary or secondary alcohols. Now if we have a look here, we can see this is number 2 here, that's a secondary alcohol group, so that means we're going to get a color change. So the color of the mixture after warming will be green. So the color changes from orange to green, but the mixture after warming will be green. Color change, question 2 here, the color change was due to a reaction of one of the two numbered functional groups, so either of these two. Identify the functional group that reacted and state why only this functional group reacted. So the ketone group, ketones don't readily oxidize, so that's not going to react. The secondary alcohol, however, here will. That will oxidize to a ketone group. So today on Flipping Science, we looked at the reactions of alcohols, and we also looked at testing aldehydes using Tollens reagent. That's it for Flipping Science today. See ya.